before we go to the next example, here's a small note about line integral over a union of curves. Now let's say our curve C consists of several curves. So this is curve C2, this one is C1. Let's try it. Let's draw another one. So this is C3. Now if C, the curve C equals to union of these three curves, union C1, union C2, union C3, then the line integral of f ds over this curve C equals to summation of the line integrals. So line integral over the curve C1 plus line integral over the curve C2 plus line integral over the curve C3. Let me draw it in red. Okay, now let's go to the next example. Now here we want to evaluate the line integral of x ds over the curve C, and our curve C consists of two segments. We have a line that goes from -2 to -2 to 0, 0, and then we have a curve that corresponds to the parabola y equals x squared, and this curve goes from 0, 0 to 1, 1. Okay, now let's do this. Let's draw a picture to illustrate this line integral. Okay, now this is a line integral in 2D space. This is x, that's x, and this is y. We have a line segment that goes from -2, 2 to 0, 0, and after that we have a parabola this is y equals x squared, and it goes from 0, 0 to 1, 1. So this is your curve C2, this is your curve C1, and equation of this line should be y equals to -x. Of course it should go through the origin, and its slope is -1. So equation of that line is y equals -x, and the equation of the parabola is given. It is y equals x squared. Okay, now this line integral x ds equals to line integral of x ds over the curve C1 plus line integral of x ds over the curve C2. Now before we solve this, we need to identify the parameterization for these two curves. Okay, now in a case like this, let's consider the path C1. Okay, now its equation is y equals to -x. So in this case, take x equals to t. T is the parameter. Since x equals to t, your y coordinate becomes negative t. So now the parametric equation for this line segment C1 equals to t comma negative t. X coordinate is t, y coordinate is negative t. Similarly, for path C2, now again we take x equals to t because x is the independent variable. Now if x equals to t, y coordinate becomes x coordinate squared, which equals to t squared. Therefore, the parameterization for the curve C2 equals to t comma t squared. Okay, great. Now let's go back to this line integral. Okay, now so I'm going to solve this line integral first, this one first, and then I'm going to do the second line integral. So let's consider the line integral in x ds over the curve C1. Now this equals to, now your C1 is, okay, let's copy this. Okay, your x coordinate equals to, now on C1 your x coordinate equals to t, and then here we should have C1 prime of t, magnitude of C1 prime of t dt. Okay, and we need to figure out the limits. Okay, let's calculate C1 prime. C1 prime should be 1 comma negative 1. Therefore its magnitude should be square root of 1 squared plus negative 1 squared, which equals to root 2. Okay, now what are the limits of t? Now if you go back to the figure, this is your initial point. This is the terminal point for curve for the line segment C1. Okay, now to get the initial coordinate negative 2 comma 2, my t should be 2. T should be negative 2. Sorry, t should be negative 2 because x coordinate should be negative 2, y coordinate should be positive 2. Therefore, this a value, so let's make this note. T goes from negative 2 to 0. Because when t equals to 0, you will reach to the origin, and if t equals to negative 2, you will go to the initial point. Okay. So then this line integral becomes negative 2 to 0 t times root 2 dt. Of course root 2 is a constant, we can take it out from the integral sign. T dt. Integral of t is t squared over 2. If you apply the upper limit, you will get 0 minus the lower limit. And this lower limit equals to negative 2 squared over 2. Okay, negative 2 squared is positive 4. Positive 4 times this negative becomes negative 4. Negative 4 over 2 is negative 2. This answer becomes minus root 2. Okay, so this is the value of the first line integral. Okay, now let's consider the second line integral. So now we are going to consider the second line integral. Integral of x ds over the curve C2. Now what is C2? The parametric equation of C2 is t comma t squared. Okay. So now this line integral equals to integral what is the value of x on this curve? Well, the x coordinate on C2 is given by t, so this should be t. Then here we should have magnitude of C2 prime dt over the limits a to b. Now let's calculate C2 prime. C2 prime should be 1 comma 2t. Therefore its magnitude should be square root of 1 plus 2t squared, and this equals to 1 plus square root of 1 plus 4t squared. Okay, so now we can update the integrand. Now let's figure out the limits. Now for the curve C2, this is your initial point. For C2, and that's your terminal point. Okay, now, so what should be the range of t? Okay, so your initial point 0 comma 0, terminal point is 1 comma 1, and your curve C2 has a parametric equation t comma t squared. Therefore t equals 0 corresponds to the initial point, because if t equals 0, you will get the point 0 comma 0, which is the origin, and t equals 1 will give you the terminal point, because when t equals 1 you will get the coordinate 1 comma 1. So now we can update the limits. should be 0 to 1 t times square root of 1 plus 4t squared dt. Now this is the integral that corresponds to the second line integral. Now to solve this integral we need to use a u substitution. Let's take u equals to this complex part, which is 1 plus 4t squared. Then your du becomes derivative of this, which is 8t dt. 8t dt. Okay. So now we have t times square root of u. Instead of dt, I can write du over 8t. From this we can solve for dt. dt equals to du over 8t. Now let's find the corresponding limits for the u variable. T goes from 0 to 1. Therefore u goes from, if t equals 0, you will get u equals to 1. If t equals to 1, your u equals to 5. So now this lower limit should be 1, upper limit should be 5. Okay, now as you can see, we can cancel this t with the t in the denominator, and 1 over 8 is a constant, so let's take it out. Integral of square root of u is u to the power 3 half over 3 half. Lower limit is 1, upper limit is 5. I hope you all know how to integrate square root of u. So recall, square root of u is the same as u to the power 1 half. So integral of u to the power 1 half with respect to the u variable equals to u to the power 1 half plus 1 over 1 half plus 1, which is 3 half. Okay. Now apply the upper limit first. So you have 1 over 8 times, now 1 over 3 over 2 equals to 2/3. Apply the upper limit first. We get 5 to the power 3 half minus 1 to the power 3 half. If you simplify this, you should get 1 over, this is 4, 4 times 3 is 12, times 5 to the power 3 half minus 1. Okay, but this is not the final answer. This is the value of the second line integral. So now let's add the value of the first line integral and the value of the second line integral. One plus ds over the curve C2. The value of the first line integral was negative root 2 plus, then the value of the second line integral, which equals to 1 over 12 times 5 to the power 3 half minus 1. This is the value of the line integral over the curve C, where curve C consists of two curves. One is a line, C1 is the line that goes to the origin from negative 2 comma 2 to 0 comma 0, and then C2 corresponds to the parabola that goes from origin to the point 1 comma 1.